In Lab 1, we discussed constant velocity motion. The purpose of this lab was to construct a model of the motion of an object that is moving at the same speed without changing direction, i.e. constant velocity. This experiment observes the differences in the change in position as a function of time using two different models. The first model is the experimental model that illustrates the change in position. To model this, we used an application called Tracker that allowed us to analyze the video and extract its position and corresponding time. The second model is a predicted change in position that was created using the same ideal conditions as the experimental video. This functions as a theoretical model and was created using VPython and an application called GlowScript. The two different methods were analyzed to see how accurately the actual lab experiment was carried out in comparison to the theoretical model. The main concept that this lab was used to illustrate is Newton's second law. This law states that in order for an object to accelerate in any direction, there must be a net force acting on the system. Explaining this law in terms of momentum, the above statement would simply be modified to say that the change in momentum requires a net force to act on the system. The formulas that accurately illustrate this phenomenon are the updated velocity and the updated position formulas. The velocity formula says that the final velocity is equal to the initial velocity of the object plus the net force of the object divided by the mass times the change in time. The updated position formula states that the final position of the object is equal to the initial position plus the average velocity times the change in time. It is important to note that the net force acting on the object is zero, indicating that there is no acceleration or change in momentum of the object. From this, we can conclude that the average velocity is equal to the final and initial velocity. When we open our video in Tracker, we have set the origin as the center of the ball, and the ball is moving to the left, which we have established as the negative x direction. When we play the video, Tracker collects the position versus time data moving in the negative x direction. Before we open our code to run the theoretical model, we must first make some calculations, based on the data table given by Tracker. First, we need to specify the initial position of our ball by taking a look at the position of the ball at time equals 0. Next, the initial velocity is calculated by dividing the change in position by the change in time from point 1 to point 2 using this table. From this, the initial velocity is given as negative 0.755 meters per second. Because the velocity of the ball is constant, this initial velocity calculated here is the velocity of the object throughout the experiment. Before running our program, we first need to make some changes in order to make the program specific to our particular experiment. First, we change the mass of the ball to indicate the average mass of the regular tennis ball, which is about 0.213 kilograms. We also input our initial position according to the data given in Tracker, as well as the initial velocity that we calculated in the previous slide shown here. Next, we also needed to stop the code at t is less than 0.635 seconds, because that is the time of the last observation that we made. We also had to change the f-net vector to equal 0, because if the velocity remains constant, meaning b final is equal to v initial, then f-net should also be 0. We also changed the velocity and position equations to the same format as the updated velocity and updated position formula shown in slide 2 of this slideshow. When we run this program, we see that as time increases, the position of the ball increases in the negative x direction, while the velocity remains constant. When comparing the model to the experimental data, the lines are very similar. However, we see that the line for the experimental data shown here in blue is slightly higher than the line from the model data shown here in orange. This could be due to the major assumption that we made at the beginning, that there is no net force acting on the ball. The lack of control of our surroundings indicates that there could have been several forces acting on the ball that remain unaccounted for. This likely accounts for the small variation between the experimental and the model data. When this experiment was filmed and I set the axes on Tracker, I set the positive x direction towards the right. I had my ball moving from right to left in the negative x direction, which explains why there's a negative slope on the graph, as the ball is technically moving to the left, as the ball is technically traveling in the negative y direction. If the x-axis were to be flipped, meaning the ball moving to the left was now the positive x direction, the graph would also change to move in the positive y direction and give a positive slope. Because the net force is equal to 0, our experimental results are very similar to the results given by the theoretical model. However, as mentioned previously, it is impossible to simply conclude that there is no net force because we do not know how many forces were added together to give us that result. There are innumerable net forces that could have potentially been acting on the object, such as friction or air resistance, and it would be very difficult to predict the combination of forces that yielded an overall net force of 0.